Hey everyone, today we're going to be talking about VGA. That's right, that connector that's just been sitting there staring at you saying, do fun things with me on the Go board. We're finally going to learn about how to talk VGA and drive some video data to your monitor. So let's get started. First, just a brief history of VGA. It was introduced in 1987. It looks like this connector here, the blue connector that you see if you've plugged in a computer anytime in the last 30 years. It is an analog interface, so the new standards like DVI, HDMI, DisplayPort, those are digital interfaces, and those are going to be replacing the old analog interfaces like VGA for a number of reasons. They're usually capable of more data. The digital interfaces look better. I don't know if you've ever hooked up a VGA monitor in like 1920 by 1280, but you can kind of see some of the blurring from pixel to pixel. I notice it when I have a DVI monitor next to a VGA monitor, both running like a 1920 by 1280 display. The DVI just looks crisper, it looks better. And that's because it's a digital interface versus VGA, which is the analog interface. But the nice thing about VGA is that it's very, very simple to use, and since it's so simple, we're going to use it to learn with. People have asked me before, why didn't I put an HDMI connector on the Go board? And I considered it, but it's just too complicated of an interface. The protocol is complicated. It's expensive, actually, so the price of the Go board would have gone up. So for those reasons, I chose to just keep things dead simple, learn about VGA. That's learning about video and learning about how video works. Getting into that mindset carries over to HDMI. The protocol changes, so everything you learn from this project is still portable to other projects that use HDMI or DVI, but the concepts really is what's important here. So speaking of those concepts, the VGA monitor that you are looking at is this green part here. And that's called the active area of the screen. So if you're using a 640 by 480 image, this is 640 columns by 480 rows, 1920 by 1280, whatever your resolution is of your VGA monitor. This particular project is going to be focused on a 640 by 480 display. To the right here, you might not know about this, but it's here. This is called horizontal blanking. This is actually time when there's data being driven to the VGA monitor, but nothing is actually being displayed. Vertical blanking, same concept. This whole bottom box here is vertical blanking box. This is when data is being driven to the monitor, but nothing's actively being driven. So active area, inactive area right here. And one thing this is trying to point out is that there is these notions of H-sync and V-sync. H-sync is horizontal sync, V-sync is vertical sync. And those are signals that I'm using on this project to tell you which part of the screen that you're in. So if H-sync and V-sync are both 1, you're in the active area. If H-sync is 0 but V-sync is 1, you're in horizontal blanking time. If H-sync is 1 and V-sync is 0, you're in vertical blanking time. And if they're both equal to 0, then you're in this horizontal and vertical section down here in the corner. So it's an easy way to keep track of where you are in the image. We'll see how that works when we actually get to the code. Okay, so here's a more detailed version of the exact same slide that I just had up. The active area is, like I said, in the Go board project we're going to be doing 640 columns, 480 rows. The inactive area here, I just made it all gray, but again, horizontal blanking, vertical blanking. And for that, that's actually going to be 800 columns by 525 rows for that. And the math behind this is actually shown how do I get these numbers in the code, but these are pretty standard numbers. Remember the Go board clock, the main clock on the Go board is 25 megahertz. So you need to do some math using a 25 megahertz clock. How can you get to a 60 hertz frame rate? So you need to set these columns and rows numbers appropriately in order to get to a 60 hertz frame rate. This on the side here shows what VSync looks like, kind of if you were to flip it on its side. So it's going to be high during the active area and during this horizontal blanking time. VSync is going to be high, and then it goes low during the vertical blanking time down here. And the H-sync signal is going to be high for this active time and for this bottom vertical blanking time, and then low for this rectangle here. So same information as the previous slide, a little bit more detail about the actual image format that we're going to be using for this project. And then there is one last concept to talk about, which is front porch and back porch. Now, VGA is a little bit frustrating in this regard, in my opinion, because front porch and back porch are basically required to center the image on a VGA monitor. And my understanding of front porch and back porch have to do with the old way that a cathode ray tube, TVs in the older times used to work, when there was actually a cathode ray that would sweep across the screen horizontally, and then it would have to go back to the beginning of the line and go down one row and sweep across the screen horizontally again, kind of like a typewriter, like scanning across the screen really, really fast. So fast that your eye doesn't actually see it, but not fast enough that it's instantaneous. So there actually is, like, the amount of time it takes, if you have a typewriter and you get to the end of a line, you hit return, your typewriter goes like ding and like slides back to the beginning of the line, and the cathode ray tube would have to do something similar, and so you'd have to allow for that to happen. You have to allow some time for the cathode ray tube to actually draw the image. And so this concept of front porch and back porch needs to be utilized here to draw the image, to center the image correctly. And all VGA inputs require this, and it's a little bit of a pain to deal with, but these are the numbers I'm going to be using for modifying the sync pulse to include a front porch and a back porch. I do just want to point out some math behind this front porch, sync pulse, and back porch stuff. You'll notice that the whole area, let's just look at the horizontal column for now. The whole area is 800 pixels. The visible area is 640 pixels, which if you do 800 minus 640, that leaves 160 pixels in the inactive area of the screen. If you add up 18 plus 92 plus 50, you get 160 pixels. So this is showing the entire time of the horizontal line that as it's being drawn. What this is doing is it's actually modifying the sync pulse that we saw here, this H sync pulse, where it was inactive for the entire 160 pixels. Now we're actually going to be only having it be inactive for 92 pixels. So we're actually going to increase the time when the sync pulse is active by 18 pixels on the front and 50 pixels on the back. So what that's going to end up doing is it's going to increase this H sync pulse by, 18 pixels here. It's going to be low for 92 pixels, and then it's going to be high for the last 50 pixels. So that's just going to be adding the front porch and the back porch in. It's required to do that, to draw the image centered on your VGA display. And then same thing for the vertical line. So if you look at this column, there are, 45 inactive lines. 10 plus 12 plus 33 is 45. And we're going to be modifying the sync pulse too. So the sync pulse used to be low for 45 lines. Now it's only going to be low for 12. It's going to be high in the beginning, the vertical front porch for 10 lines. These are lines, by the way. And it's going to be high for 33 lines on the back porch. And then there's the other question of how to convert the VGA signals from digital, because the FPGA is a digital system, to an analog voltage. And the way that this is actually working, I show on the schematic here, but basically I just set up voltage dividers on the Go board and get the right voltage to the VGA monitor, just using a simple voltage divider. So it's kind of a crude way to do it. You probably don't get the best color replication with this, but I mean, we have 8-bit color, it's 8 bits total, so it's up to 512 colors available. You probably wouldn't want to try to drive, Windows 10 using this Go board. It wouldn't look very good, but for this particular project, it's simple enough. And like I said, goal was to keep it cheap, so resistors are almost free. So this is the easiest thing to do. This is part of the Go board schematic, by the way, which is freely available to you if you want to take a look at it. Okay, so that's the brief introduction to how VGA works. I think the most complicated thing about the VGA interface is the sync porch stuff, the front porch and the back porch stuff. So if you want to do a little bit more research to exactly how that works, that's up to you. I will provide the code for that. That's this module down here, where I just modify the horizontal and vertical sync to add the porches in, so that you get your image displayed centered correctly. So the project that we're going to be doing is outputting test patterns to the VGA port on the Go board. So simple test patterns. The test patterns that I chose was like a screen that's all red, a screen that's all blue, a screen that's all green, and then like a checkerboard pattern and a color pattern, kind of like the color pattern you would see if your TV loses a cable signal or something. So you should have that be selectable by the computer keyboard. And this is just building on the previous project where we had the UART receiver and the binary to 7-segment converter. So the previous project was this module, and this module, the receiver, the transmitter, and the converter. That was it. And it was driving the 7-segment displays and showing you what key you pressed. This project is going to be adding 3 new modules: a sync pulse generator, a test pattern generator, and a VGA sync porch, and that's going to be driving the VGA display. So this builds on the complexity of the previous project. The next project is actually going to be the game of PONG, which is a lot of fun. And what that's going to be doing is replacing this test pattern generator here with PONG. So the whole all the Go board tutorials kind of build on themselves, which was somewhat intentional. So yeah, I thought that through, and it makes it more fun. So you can actually see how your code, if you make it modular, you make it portable, you make it reusable, and that pays off at the end of the projects because you get to use your code over and over again. All right, so I think I should probably talk through in just high level what these 3 blocks are going to be doing here. The sync pulse generator is your H-sync and V-sync pulse generator. So H-sync and V-sync from this here. In this case, we're going to be generating H-sync that's going to be high for 640 clocks, low for 800 minus 640, 160 clocks here, and then a V-sync that's high for this entire time for 480 rows, and then low for the last, 45 rows of the frame. So that's the whole purpose of this module, is just to generate this V-sync pulse here and this H-sync pulse here, such that you use the 25 megahertz Go board clock and you get a 60 hertz image coming to your monitor. The test pattern generator itself takes the input H-sync and V-sync, and then it knows, based on those 2 signals alone, where you are in the frame. So it'll actually count the rows and columns of where you are in the frame. Row 00 is the top left corner. Row 0, call 0 is the top left corner. Row 479, column 639, if we're indexing from 00, is the bottom right corner of the active part of the image. And based on that data, where you are in row and column, you're going to be able to, what you should do is you should just draw whatever pattern you like. Like I said, I chose a few different patterns, which I will go through. And the last piece of code here is this VGA sync porch, which is going to actually modify the horizontal and vertical syncs to add in the front and the back porch. And those timings come from this here. I encourage you to try to figure this project out. This is definitely the most complicated project so far. It introduced some new concepts, but this is a fun one. So definitely think it through. I will show you my solution, should you want to look at that. I will be starting with the Veralog solution and then going to the VHDL solution after that, and showing you the results of the VGA test pattern generator. So let's get started. This is the Veralog section of the code. If you want to skip ahead to the VHDL section, you can do that now. So first of all, navigate to edaplayground.com/x/U lowercase c lowercase t. And that is the Veralog test environment that we're going to be using to simulate these modules and just make sure that everything is working smoothly. So I'm going to make this a little bit bigger. We can see everything. I do want to first start with the VGA sync pulses, which was the very first module in that chain of 3. It was VGA sync pulses was first, test pattern generator was second, and the VGA sync porch was third. What this module is doing is generating, the sole purpose is to take in a clock and generate H-sync and a V-sync. And I actually also generate a row and column counter, but I don't think I actually use these in this project. And this is really simple. All it's doing is looking for the rising edge of the clock, the positive edge of the clock, and checking to see what the current column counter is. If it's equal to total calls minus 1, so in this case 639, then set the column counter back to 0, and then check to see where we are with rows. If rows are equal to the total number of rows, we're at the end of the frame. Otherwise, we count up to the next row. And the assignment here for the H-sync just says if we have this notion of the total area and the active area. The total area is the total area of the whole frame, 800 by 525, whereas the active area is just the 640 by 480 that we are displaying. And H-sync and V-sync, like I've said before, are only high during the active area. And that's it for that module, so that'll generate the sync pulses that the other modules are going to be using. I just want to show this module quickly. The purpose of the sync to count module takes in an H-sync and a V-sync, and outputs an H-sync and a V-sync and a column counter and a row counter as well. So it just keeps track of where we are in the frame. And this is really convenient because a lot of times you're going to want to know where you are in a frame for different modules. I used it here in the test pattern generator down here. So that tells us where we are in the frame. I also used it in PONG in the next project. So it's nice to have things like this wrapped up into just a little module you can instantiate quickly without having to generate. I mean, it's not a lot of code, but it's a couple always blocks. And, this is the type of thing you might make a simple mistake on. So it's best just to wrap this up once and instantiate it wherever you need it. For the test pattern generator, takes in an H-sync, takes in a V-sync, and it takes in this notion of what pattern we're going to be using. And this is going to be fed directly from the UART. So the UART is going to choose the pattern, and that's going to be driving the red video, green video, blue video, and as well as the output H-sync and V-sync. This output H-sync and V-sync are the ones that are the full active area before it's been modified by the Porch modifications. This module here will take this H-sync and V-sync and modify them to include the front and the back Porch. So this isn't too bad. It's a little bit long because there's a lot going on with the different test patterns, but I commented it up. So test pattern 1 is all red. So all it does is I created an array here. Maybe that's worth talking about. This is the first array that we've seen in Veralog, where the width of the array is this first number in the brackets here. So this is video width minus 1 down to 0. And then this on the back end here is the depth of the array. So in this case, there's 16 indices into this wire here. And what that is enabling me to do is just to, with one signal, keep track of a bunch of different test patterns. Rather than having to do like pattern 1, pattern 2, and create a bunch of test patterns, it's just one signal. It's a big array. So we index into the array like this, where for pattern 0, we're going to disable all of it. Boom, just turn it off. Pattern 1's all going to be red, and that's using the conditional assignment operator just to check where we are in the frame. If we're in the active area if W call count and W row count are less than the active area, then we're in the active area of the frame. Then we're going to be setting the pattern red just to all ones. And green and blue are going to be set to 0 all the time. So when I first did this, I kind of thought you could just do this. Like you could just say that, pattern red just gets 1s for everything, for the all time. And that actually doesn't work. You have to drive anything that's non-zero can only be driven to the VGA monitor during the active portion of the frame. So that's what the purpose of this module of this code here is just to see that we're in the active area of the frame and only illuminate the red color if we're in the active area. So that was a learning experience for me. For green, it's the exact same thing. We just replace red with 0. Blue, same thing again. Green and red are both set to 0. So You can make different combinations. If you wanted to set like green and blue to be 1s for everything, you can see what kind of colors you can draw. Pattern 4 is the checkerboard. That's kind of like a game of chess, kind of. And the way I did that was just, well, you can figure it out. Well, how did I do that? Take a look at it. See if you can figure it out. And then finally, I did some color bars here, and you can look at this code and see exactly how this works. This isn't too complicated. There is a multiplication in here, which I should mention that multiplication inside of an FPGA, like especially multiplying something by 7, is usually you can't synthesize that very well, but in this case, W underscore bar width is set to a constant. Active calls divided by 8. So the synthesis tool actually knows what this number is going to be, so it's actually doing just a comparison to a dynamic signal with a static constant. So that's going to be okay for synthesis purposes. Something to think about. And then we have a case statement here which just chooses the output pattern based on the input from the UART. So that's pretty much it for the test pattern generator. And finally, there's this sync Porch, which, as I stated, just modifies the input H-sync and V-sync to include the front porch and the back porch. I do have some constants or parameters here, and these should be the same ones that I showed in the table previously. And that is it. There is this EDA development environment here, and I did write a test bench because I'm responsible. And if you run the test bench, let's see. So first of all, I instantiated the sync pulses module and the test pattern generator itself. I didn't instantiate the sync Porch module because it's kind of hard-coded for a 640 by 480 image, and I didn't want to have to run a full 640 by 480 image through the test bench. You'll notice that I changed the total. Now it's only running a 6 by 10, or 10 by 6 rather, total image size and an 8 by 4 active image size, which just keeps the test bench size down. I guess I need to log in. Am I not logged in? The reason to keep the constant small is just to allow the simulation to run quicker. So let's do that. Let's run it. What am I using? Riviera. That one seems to work pretty good. Click on Get Signals, and what should we look at? How about the unit under test? VGA sync Porch. We're going to look at only these signals are interesting. And the test pattern generator. Look at that. All right. Just a quick cursory look. I guess I'm not doing anything with that. But the test pattern generator does, you do see the H-sync is toggling, the V-sync is toggling. It looks like things are working correctly. And the blue, green, and red video are changing as well. So, and what did I give it for a test pattern input? 5. So that's drawing the color bars one, which is the most complicated test pattern sequence that we're drawing. But the rows are counting correctly. The columns are counting as well. So things appear to be working well. And lastly, the actual top level module is going to be building on the previous project. And I'll just show that quickly here, what that looks like, where we have the UART receiver, the transmitter, we have the 7 segment displays, that's nothing new. Down here we go. The VGA test patterns, we're going to instantiate the sync pulses module, which generates the H-syncs. Those go directly into the test pattern generator. And the test pattern index is going to be setting up which test pattern we're going to be using. The way I did that was I just looked to see when the receive data valid from the UART was high, and when it is, we just register in the least significant nibble of the received data and just store that into this TP index. So when you hit a button on the keyboard, it's going to change the test pattern that's being displayed. Output of that is going to be your H-sync and V-sync, modified H-sync and V-sync, as well as your red, green, and blue video. That goes straight into the Porch modifiers. Output of the Porch modifiers, we break up into the OVGA red underscore 012, green underscore 012, blue underscore 012. And that is the 3 colors that I showed on the schematic that gets driven to the VGA connector on the Go board. So that will complete the top level module of this project. If you want to look at this code, I will put a link in the YouTube description to nandland.com where this code is hosted, so you can take a look at it yourself. So that'll do it for the Veralog section of the code. I'm going to be talking about the VHDL section next. Feel free to skip ahead and see the result of your labor. For the VHDL section of the code, if you navigate to edaplayground.com/x/6, capital H, lowercase u, lowercase n, you can see the test bench code on the left and the VHDL modules on the right. I'm going to move this over so we have more room to look at the code and go through how everything works. So again, like I said, the first module is this VGA sync pulses. And the sole purpose of this thing is just take in the 25 megahertz clock, generate 640 by 480 video data. And the way that works is just a simple process that counts up and keeps a call count and a row count inside. When the call count gets to the end, the total number of calls, it resets back to 0, increments the row count by 1. When row count gets to the end, it resets to 0, and you're at the end of the frame. This process will just count forever. And outside the process, I combinationally generate hsync and vsync based on the current count values for rows and calls. So if you're less than the number of active calls, then hsync is valid. If you're less than the number of active rows, vsync is valid. Otherwise, they're 0. And I also passed out the current column counts and row counts just in case the next highest level module needed them. But if you don't have these call count and row count handy, I have a sync to count module, and the sole purpose of this guy is just to pass in an hsync and a vsync, and knowing the total size of the frame, what is the current column and row that were indexed into this particular pixels. So the way this module works is very similar to the other one, where it just looks at the clock. If we see a frame start, which a frame start is the condition when vsync equals 0 and when the previous value of vertical sync is 0, but the current value is equal to 1, we know that we should reset our counters because we're at the beginning of the frame. And when that happens, we're going to start incrementing the call count and the row count back again from 0. So this is just a nice way to wrap up some functionality that I find myself using pretty often in video applications, where I have an hsync and I have a vsync, and I want to know where the heck I am in the middle of the frame. And rather than having to generate all this logic in a bunch of different files, it's nice just to have it in one file, wrap it up. It's got 2 input generics that you need to set, but other than that, you can just plop it in and use it wherever you need it. So very handy to wrap code that you use in multiple places in like this. The output of the VGA sync pulses is your OH sync and OV sync, and that is going to get fed right into the test pattern generator. Let's look at the entity for the test pattern generator. We have video width, which I set to 3 because we have 3 bits available to us. Total calls, total rows, active calls, active rows, which are going to get set by the higher level module. Additionally, we have our 25 megahertz input clock. We have our test pattern. This is coming from the UART, and the IHsync and IVsync. The output is going to be the output hsync, output vsync, which are not necessarily aligned in time with this input hsync and vsync. So if this module takes 2 clock cycles, these are going to be 2 clock cycles behind these 2. But the nice thing is that if this module takes 10 clock cycles, you no longer, the downstream modules don't care about the delay that it takes. So this is a convenient way to just keep your video pipe flowing. We also have the red video, green video, and blue video as outputs as well. What next? This is probably the first time we've seen a 2-dimensional array, or an array in general. Well, standard logic vectors are arrays, but this is the first time we've seen a user-defined array in the Go board code. So I created a new type here. I called it T underscore I use for types. And it's an array type, 0 to 15. Notice it's not 15 down to 0. It's an up count. It's an upward count. And the array type is standard logic vector G video width -1 down to 0. So this is just you can index into this. And the reason I did it this way is it just makes these signals, pattern red, pattern green, pattern blue, such that I can index into them. Pattern red, parentheses 0, pattern red, parentheses 1. That's test pattern 0, test pattern 1. It just keeps the number of signals that I need to create down to a minimum if you use arrays. So it's a handy way to do it. Let's see, what else? We're going to be, that's just a process to register the input sinks to align with the output data. So then I'm going to be going through each pattern individually and setting up this pattern red array based on which test pattern we're going to be driving out the go board. So the very first one, pattern 0, everything's set to 0. All of pattern 0 is just off. Pattern 1, everything is red. So pattern red at index 1 is going to be set to 1, but only during the active area of the screen. That's what this when is doing. It's saying only when the current column that we're in is less than the active column and the current row that we're in is less than the active row index, then set the output to 1. Originally, I actually had this, when I was first developing the Go board, I had it like this, where, pattern red 1 would always be 1. And to my surprise, that didn't work. The VGA interface apparently, or at least my VGA monitor, maybe some other monitors are different, but my monitor didn't allow me to do this. It actually it required that the pattern changed and went to 0 during the inactive portion of the frame. So that's what I had to do. That's what this is doing here. It's turning it off during the inactive portion. For green, it's the same line of code except that I'm driving pattern green, pattern at index 2. Index 3, I'm only driving blue. You could create other colors here, like if you drove red and blue, I would assume you'd get like a purple color. So you can play with that, see what kind of colors you can get. Checkerboard, white and black. This is using the XOR bitwise operator, which is kind of fun to do some checkerboard stuff. I won't go through exactly how this works. You can take a look at it and try to figure out how that works. Pattern 5 is color bars. This is kind of a neat one. It looks like a color bars when the cable goes out. And this is just using a pretty large combinational decode statement here where you have the bar select gets 0 when this condition is true, else 1 when this condition is true, else 2, else, So this is a long carry decode chain when it gets synthesized, but it does meet timing without a problem, so that's nice. This is probably the longest the longest carried combinational statement that I've written yet, but it does synthesize, no problem. And then I just set up the individual output patterns for that. And then down here there's this case statement where I take the input pattern from the UART, and based on what the UART is telling me to display, I choose 0, 1, 2, 3, 4, 5, 6, and that's it. HSync and the OHSync and OVSync are always being driven, but you are changing which video gets driven out. The output of that then gets modified by the sync Porch module, which is very similar to the sync generator, except that now we're just modifying the existing sync pulse by these constants here: front porch horizontal, back porch horizontal, front porch vertical, back porch vertical. And these numbers are the ones I showed in the PowerPoint. So this just modifies the output of this is just the same video that we had previously, but with a modified HSync and VSync to include the front porch and back porch. And that's it for the code. So I do want to just show the test bench as well while we're here. The test bench is going to be instantiating the sync pulses module and the test pattern generator module. It doesn't instantiate the sync porch module, and the reason is because these constants are hard-coded inside of here. Where is it? Right here. These are hard-coded. I could have moved them to generics. I didn't. If I had put them as generics, I would have been able to change them and make this run a lot faster. But my total image size for this test bench environment is a 10 by 6 image with an active area of an 8 by 4. So it's not a lot of pixels being drawn, and that's just to speed up the simulation. So if we run it, we can take a look at the EP wave, make sure that things are counting and looking to be correct. This isn't a self-checking test bench. This is just to give you a visual indication that things are working approximately how you would expect. So we'll get some signals. Let's see. Synced account is probably good to look at. Let's look at those. And the test pattern generator as well. All right, so we see HSync is being humming along here. VSync looks like it's working as well. So when VSync goes from low to high, and HSync goes from low to high, this is the beginning of a new frame right here. I can tell you that right now. This is the active portion of the frame when HSync and VSync are both high. And then here is this low vertical blanking part down here. The row and column counters you can see are counting away. Looks like those are working correctly as well. So it looks like the whole frame is 0, 1, 2, 3. So 4 active rows, 2 inactive rows. And then down here is the test pattern generator, where the blue video, the green video, and the red video are all toggling. And I set this to pattern 5, which is the color bar pattern. So that's what this is all represented by here. So this looks good. Things are toggling away. One last thing to look at is the highest level module. So the highest level module is here. And this is very close to the previous module where we had the UART receiver. We have the UART transmitter. We have the binary to 7 segment. I didn't even bother to remove these. It's just easier just to keep them in. And then down here is the new stuff, the VGA test patterns. So the very first thing is to register the received data byte, the lower nibble of the received data byte, and use that as your test pattern index. And you're doing that when the data val pulse is high. And that just registers it so that if this data changes or goes away, then we still know which test pattern to draw. VGA sync pulses is next. The whole purpose of that is to generate your HSync and VSync. Those get fed right into the test pattern generator, which generates based on which test pattern we have selected, the video, the color data, and the output HSync and VSync, which get fed into the sync porch. So this is just a big video pipe, module to module to module in order. And that just modifies the HSync and the VSync to include the front porch and the back porch, and that gets driven right out to our pins. So again, these pin names are important again, so do match those names because those are in the constraint file. And that's it for the VHDL section. Next, I'm going to program the Go board and show you the results. The Go board has been programmed, and now I can hit the keys on the keyboard and change the number being displayed there. So that's working. The UART is showing what I am typing, and my monitor is changing. So that's test pattern 1, it's red, test pattern 2, green, test pattern 3, blue, test pattern 4 is the checkers, test pattern 5 is the pretty nifty color bars. So that concludes this tutorial for the VGA introduction. The next tutorial is going to be taking things to the next level. We're going to be doing PONG, which does build on the concepts that we showed here. And PONG is going to be the last Go board tutorial that I'm going to be doing. So I hope you've enjoyed it thus far. Let's get ready to wrap things up.